Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a very nice quintic equation with complex numbers. And some of you are probably questioning, like, isn't this problem super easy? Z equals 1. Yes, that is the trivial solution, but we're also going to be looking at the non-trivial solutions, and I'll be presenting two methods, and you're going to get to decide which method is better or which one you like better. All right? I'm not going to tell you my preference because I don't want to kind of mislead you or be biased, because I'm always biased, right? Obviously. So z to the fifth equals 1. So we're going to be solving for z. How do we solve for z? Let's start with the first method. First method involves a lot of heavy algebra, so bear with me while I do this, but this is fun. So I'm going to go ahead and subtract 1 from both sides to set the whole thing equal to 0. Notice that a to the n minus b to the n can be always factored if n is an integer. And a to the power n plus b to the power n can be factored when n is odd. When n is even, it can't be in the real world. But wait a minute, isn't this channel all about complex numbers? Yes, but we're going to do some stuff with real factors as well. Okay, so we're going to try to keep it real for a while. So we don't have to worry about this. Let's worry about this. How do you apply it to this scenario? Well, there's a formula for this. You hopefully know that. It goes like this: a minus b, a to the n minus 1, plus. And then what you do is you start with the the highest power of a possible to get an a to the n, no b, and then you reduce the power of a while introducing b into the equation, and you end up with b to the power n minus 1. Everything is positive in the second factor, which is important because with the a to the n plus b to the n, the factors or the terms will alternate. Plus minus, okay? So be very careful. This is kind of like an easy version in that sense. But let's apply it to z to the fifth minus 1. Here in this case, I consider this 1 to the fifth power, so that I can factor it as follows: z minus 1. The first factor, once you write it correctly, the second one is going to be fairly easy, z to the fourth, and then the rest is just going to be powers of z, and in a descending manner. Why just powers of z? Because 1 doesn't have to be written. You see, that's the good thing about having 1 here. So z cubed, z squared, z plus 1 equals 0. Awesome. Now we know that, hopefully, right? From here, we're going to get z equals 1. That was the obvious real solution. That's the real deal. But we're going to be focusing on more complex numbers, and they're going to come from here. But wait a minute. That's a quintic? No, it's quartic. This is called the quartic equation, fourth degree, and there's a quartic formula, which you don't want to know. Trust me, don't go there. Don't check it out on Wikipedia because it's just insane, okay? Huge. But there's no quintic formula, unfortunately. Maybe fortunately, who knows? If we had a quintic formula, I think that would probably be several pages long. Like, it wouldn't fit on any page, of course, but it would probably be several pages. Anyways, so how do we solve this quartic then? Yes, quartic formula is one of the ways. There's another approach to work with something like this. You can kind of try to throw everything quadratic and below on the right-hand side, and then add something to both sides to make this a perfect square. So something like this. Can I make this z squared plus 1/2 z squared? Take a look at this. What is that equal to? Let's expand it. This is going to be z to the fourth plus 2ab is going to give you z cubed plus 1/4 z squared. Nice. So I can add that to both sides to make it a perfect square. Yes, but be careful about wishful thinking, but it's part of the process. Okay, let's do it. We can add the missing term, which is 1/4 z squared, to both sides, and then it'll give us the following. We're going to have more z squared on the right. This will become z squared plus 1/2z squared. And thanks to Nadia Fan, I hope I said it right, for this beautiful method, because that's how I learned it. And here we're going to be getting something like -3/4 z squared minus z minus 1. Now, good and bad. The left-hand side is a perfect square, but the right-hand side isn't. How do I know that? Come on, coefficient of z squared is negative. How can it be a perfect square? It's far away. But you can add something, and that thing is just mind-blowing, I think. We're going to take and add something like this. You might be like, where does that come from? It comes from YouTube comments. Thanks to Nadia FM one more time. I can't take credit. But you're going to add this to both sides. And when you do, let me tell you what happens, because this is a very long story and I don't want to bore you to death. But the rest is come from here. This part, oh, I'm sorry, I just forgot to add one. The left-hand side becomes this plus, sorry, that was supposed to be k squared, not 1. Okay, the left-hand side becomes a perfect square while making the right-hand side also a perfect square. And that's just perfect. You can solve for k, but trust me, that's going to be super time-consuming and super annoying. So you don't want to go there. Let's do something else. You know why? Because this equation is awesome. You know why? It's symmetrical or symmetric, whatever they call it, something like that. Something to do with symmetry, because the coefficients that are the same distance from the center, which happens to be this one, by the way, are the same. Beautiful. So we can kind of, oh, did I write 11? I meant it's just 1 is 1, right? Okay. So this is 1, that's 1. And these two pair up nicely. So we're going to go ahead and divide by z squared, which is the term in the middle. That gives us z squared plus z plus 1 plus 1 over z plus 1 over z squared. This is where the math magic happens. It's just beautiful, beautiful, beautiful. Don't you think? Take a look at this. Once I do that, I'm getting z squared plus 1 over z squared plus z plus 1 over z plus 1 equals 0. And you might be like, okay, what is so special about it? Take a look. This can be written as z plus 1 over z squared minus 2ab, which is 2, plus z plus 1 over z plus 1 equals 0. Now, here comes the substitution. Ta-da! Let's call this t. We get t squared plus t minus 1 equals 0. And yes, this is a quadratic with real solutions. Awesome, negative b plus minus the square root of b squared 1 minus 4ac. That's going to give us the root 5. Uh-oh, golden ratio, I smell. T equals negative 1 plus root 5 over 2, or root 5 minus 1 over 2, you can write. That looks better, right? And then the other t value is going to be negative root 5 minus 1 over 2. I don't know why I wrote the radical first in the second one, but that's okay. But this is just t. Set it equal to z plus 1 over z. Solve for z and be happy, okay? But guess what? This is going to be a lot of work. I'm going to show you the results. Let me show you the second method, because this was just the first one, right? I believe so. It took a while, but yes, it was the first method. And the second method, I think you're going to love it. But again, I could be biased, so don't take my word for it and decide for yourself which one you like better. And let us know, okay? Z to the fifth equals 1 is a very special equation, because you're looking at, ready? The fifth roots of unity. What is that supposed to mean? Check out my lecture videos if you're new to complex numbers. But this is what I mean. 1 can be written as e to the power 2 pi n I in the complex word. That is the complexification of 1. All right? So now we are left with this type of equation where we can raise both sides to the power 1 over 5. And that would give us something nice. Take a look. These two will cancel out. Z will be e to the power 2 pi n I over 5. So, okay, you're like, what is so special about it? N equals 0 will give you z equals 1. Okay, fine. But what about n equals 1? It's going to give you z equals e to the power 2 pi I over 5. That is the same thing as cosine of 2 pi over 5 plus I times sine 2 pi over 5. Thanks to Euler, we can go ahead and write this in trigonometric or standard form. Now, what is cosine of 2 pi over 5? That is cosine of 72, and 72 degrees is something like root 5 minus 1 over 4, something like that. And I think it's like this, if correct me if I'm wrong, but it should look something like that. Because cosine is going to get smaller and that should get bigger, something like that. You get the idea? But of course, there are more solutions. N equals 2, n equals 3, n equals 4 will give you 3 more, a total of 5 solutions, because we were dealing with a quintic, remember? Now let's go ahead and check the results from Wolfram Alpha first, how you factored it, right? We talked about it already. And ta-da, the the complex solutions from big old, or what's it called? Good old Wolfram alpha. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.